Notice anything strange about this backboard? It doesn't matter where I shoot on it, the ball goes in. Look at that. How does it know? My goal is to compute an optimal backboard. A standard backboard as a flat sheet isn't very optimal. Balls really only go in if you hit them within a certain region. That's why they have that square on the backboard. If I take a shot from the center and I hit over here, the ball just misses. And the same is true for most other regions. And what I would like to do is to figure out what shape I can make the backboard, something like this, so that no matter where I hit it, the ball gets directed into the hoop. It's basically the same thing from the side as well. The idea is pretty simple. The hard part is figuring out the shape, especially in 3D because it's a very complicated shape. So what I did to solve this problem is I did what's called a Monte Carlo simulation. The idea is that you simulate a lot of shots. In my case, tens of millions of shots from all different locations in the court at all different locations on the backboard. And for every shot that I take, I figure out how would I need to change the backboard location in this spot that I'm hitting so that the ball will go into the hoop. So say I have a shot coming in like this and it's coming in really fast. With the backboard as is, it might bounce off something like this and it won't go in the hoop. But what I could do is at this location of the backboard, I could change it to be this angle and it would redirect the ball down into the hoop. If you do this for an enormous number of shots from all the different locations, you can get a good idea of what shape the backboard needs to be so that the maximum number of shots go in. If you look at what I'm drawing for all these things, it really looks like it wants to be a parabolic shape. And that makes sense because satellite dishes are parabolas, and that's because they redirect all incoming electromagnetic waves or whatever to a single point. So if I have a ray coming in like this, it'll bounce to this point, same here, and for all of them. So there's a few key things to understand to get why it's designed the way that it is, and why a straight parabolic shape doesn't really work. The first is that the balls follow trajectories. When I shoot a ball in, it's coming on some curve because it's pulled down by gravity, and then the same thing happens when it bounces off the backboard. I have to account for this fact. Depending on where I hit it vertically, they'll drop different amounts. And the amount they drop is also related to the speed that they're coming in. They'll drop less if they're coming in faster. And then the other thing that matters a lot with basketball shots is where they go depends an enormous amount on the angle they're coming in. So the bounce will be some kind of reflection. If I'm coming up, it might bounce like this, but if I'm coming down, it might bounce like that. Given the difference that you can get for different shots, it seems like this shouldn't really work because if I shoot a shot like this, I need to change the angle of the backboard in a different way than if I shoot a shot like this. And it's true, you really can't support a line drive and a slow arcing shot. I had to optimize for a type of shot, and I went for kind of the average basketball shot that's arcing. Line drives are sort of a special case far out on the edge of possible shots. And even though there is this dependence on speed and incoming angle, there's a really nice thing that makes it not as bad of a problem. And that's the fact that the ball is smaller than the hoop. So for every possible bounce that a ball does, there's actually a range of bounces that will still cause it to go into the hoop. And this actually gives pretty good amount of wiggle room in terms of speed and angle that the ball comes in for a given point on the hoop so that it'll still go in. So the real question is, who is Monte Carlo and what does he have to do with backboards? I don't actually know who Monte Carlo is. I assume he had something to do with his technique, and I'll show you how I derived a backboard using it. So what I do is I choose a random location on the court, and then I take a random shot at the backboard. Then I look at where I hit the backboard, and I figure out what I would need to change about the angle of the backboard so that the ball will go into the center of the hoop. So say I change the surface at this location and to this angle, it will bounce into the center of the hoop. Then repeat this tens of millions of times, and remember the result for every single shot. So there's a really important subtlety, which is related to the fact that any given shot has multiple bounces off the backboard that will still go in. So for this shot, this bounce will go in, this bounce will go in, this bounce will go in, and basically infinitely other bounces within this range will go in. If you look at all of these bounces, they sort of form an ellipse. So for every shot, I can keep track of this range that it would go in, and what the corresponding angle changes to that location of the backboard would be that would cause it to hit those. What I'm about to say is somewhat hand wavy, but it does make sense. If I take this angle range for all of my simulated shots and I plot them on some kind of graph, maybe this is rotation on the y-axis, this is rotation on the x-axis, and this is a shot, I can do this for tons and tons of shots for that particular location on the backboard. And what this means is that if two ellipses overlap, if I were to set the backboard to this specific rotation or this specific angle, these two shots would go in. So what you can do is find the location in this chart where the maximum number of ellipses overlap. That will be the angle to set the backboard to in that location so that the maximum number of shots goes in. That's basically it. There's a bit more to it about having smooth, continuous backboards and making sure you're only getting sort of nominal, realistic shots. So say I do this for tens of millions of shots for all the locations on the backboard, and I choose an angle for every point of the backboard surface that I want. The only remaining question is, how do I turn that into a shape? So in concept, it's really not that complicated to do. So imagine this is my backboard, we're looking down at the top of it, and I calculated all of these angles that I need the backboard to be for the shots to go in. All that I need to do is figure out what shape I can bend it into so that the surface at all of these locations is those angles. Doing this in 2D is pretty easy. Doing it in 3D is actually more challenging, but what I ended up doing is a least squared fit. I was having a hard time getting an exact fit that was smooth and continuous, and that just involved solving a very big matrix. So if I do this in 3D and I get some shape, it still won't be quite the right shape. And that's because of one other important subtlety. It's kind of hard to explain, but I think I can do it. So imagine that this is my backboard and the hoop, and this is the backboard that I calculated so that all the balls would go in. You have to remember that I was using the original backboard to compute these angles. So if I have this shot and it bounces like this to go into the hoop, where this ball goes is relative to where it bounced. And if we were using the original backboard as the location to compute the bounces and the angles, it would actually go like this. This will cause many of the shots to miss or to at least go into the wrong spot. It creates a actually chicken and egg situation because I need the shape of the backboard in order to calculate where the ball goes, but I need to calculate where the ball goes in order to calculate this backboard shape. So it's kind of nasty. What I did this once and I calculated the backboard, which still wasn't right. Then I used that backboard as my backboard and reran the simulation. What ends up happening is you get a slightly different backboard, which is closer to correct. Then you can do it again and you get a backboard that's less different, but still different. And then eventually it converges. So this is one single shot, so the player is invisible. The blue is the computed backboard that we would need. And this is what the shot would do if it hits the upper right corner, and then the red square is the original backboard. All right, and if you run my funny little program, this is what it spits out. And you can ignore the fact that it's on this big block of material. That was just how I made it. So the first thing that I did is I cut the mesh in half because it's symmetric and it's a lot easier to work with only half of it. Looks pretty cool. So let's try it out. I can't wait to see this thing work its magic. What? Why? So for some reason, it looks like this backboard, instead of always making the ball go in, basically always bricks my shot. It seems like it's always hitting the front of the rim. I gotta see what's up with that. On the plus side, it does look like it's directing the ball to the rim the way that I want it to. It's just not exactly the way that I want it to because I need to go into the hole. I just realized that I have a pretty big error in my computation. And the error is that I'm not accounting for the radius of the ball. Basically, the calculation I'm doing is I'm looking at where the ball hits the wall and then the trajectory that it'll follow according to whatever angle the backboard location's at, and then where it lands. And the distance that I'm computing the ball going is from the backboard surface to wherever it lands, but the ball stops here, the center stops here. Basically, the net effect of this is that I brick every shot because it directs it into the rim, the front of the rim, because the ball's 2 or 3 inches further away than it needs to be. For the moment, I can patch this just by estimating the size of the ball. So it's about 5 inches. If I move the hoop forward 2.5 inches, which is the radius, it should correct the issue. But I would rather have it be the right shape to go in with the hoop nominally where it should be. But let's give this a try. Okay, the hoop has been moved out by about the radius of the ball, and this will hopefully fix the nothing but brick problem that I was having. That's more like it. You can tell I'm really good at sports by how I throw the ball. But it's actually really hard to not aim at the center of the hoop. I've been trained my entire life to throw it at the center.